Shen from Scroll. Today I'm going to share some of the challenges we encountered when we are building the zkEVM and the zkROP, and I hope I will be have some insight to everyone who want to learn more about the Scroll and then about zkEVM and how zkROP works. Okay, so what is Scroll building? So Scroll is building an EVM equivalent zkROP to scale Ethereum as a layer 2. And then what does EVM equivalent means? That means we'll be compatible for all of the EVM codes that has been using to execute all of the transactions on the Ethereum chains. And that means also that indicates that all of the smart contracts that now deploy on the Ethereum layer 1s can be seamlessly, without modifying any code, you can deploy on the Scroll. That's the powerfulness of the being EVM equivalent. So that developers doesn't need to rely on any need to learn a new language or need to use some of the plugins into your compilers to compile your code to a different architectures. So before I dive into any technical details, I want to first share some of the principles we believe in when we're building the zkEVM and the zkROPs. So first of all, we believe that all of the blockchain projects, especially the layer 2s, should be developed through a community-driven approach. Now, what does that community-driven approach means? So for Scroll, we are building our circuit all open source from day one, and we're collaborating with all of the community members to contribute to the same code repo. And we're been collaborating with the privacy scaling exploration team, the Ph.D. team from the Ethereum Foundation, and from the day one. And also there will be other community members here to join the whole the effort to build the zkEVM together. And that means all of the code, the design, it has been discussed within the community, and it has been peer reviewed to guarantee there's no bugs, and then there'll be a more secure and a better design for the community. We are also using an open source proving system called Halo 2 that's being developed by the Zcash. Besides of building with the community, we are also outreach, doing a lot of education to the public by teaching people how to use the Halo 2 to build circuits. We're teaching some of the sessions with the 0xPark group, and then to educate people how to write Halo 2 circuits. And also being running some auditing sessions to teach about the architecture of the zkEVM, how should you build zkEVM to make it secure and how to make it work. And second, we also believe that building the blockchain layer 2s need to have the security first in your mind, and then have a steady release, not rushing to become the first. I think all of the zk rollup and the zkEVM, there'll be a very long run game. It doesn't mean a first, that doesn't mean anything. I was thinking, so I think that we need to guarantee the security, guarantee the reliability, so that people will trust the zkROP will work eventually. So to be pay more attention to the security in the Scroll, we are paying a lot of attention to the auditing. So we have the auditors to look carefully, probably multiple auditors, and then iteratively looking at our circuits, the bridge contract, and then all the node implementations. And then internally, we also build an in-house security team so that we can review our code internally. So sometimes the internal team will have it will be keep reading the code and have different eyes of engineers to look at the code. So to give an example, the Zcash previously found critical bugs, and then the bug is found by the internal team members inside their own teams. That means it's very powerful to have an in-house security team to look over your code and then keep iterating and then over and over again to make sure there will be bug free. And then third things we believe in is the decentralization. So I think a lot of people believe that decentralization may be not important in the layer 2, but we don't think so. I think the decentralization is one of the key characters for the blockchain to be censorship resistant. And then that also means you need to as a layer 2 in the future will become the execution layer. So I think the 90% of execution will be happen on the layer 2s. So it's also important to make sure that the layer 2 will inherit the same guarantee that Ethereum provides as a layer 1. So that means also we need to be censorship resistant, and then the decentralization will be an important part of that. So for Scroll, we are committed to decentralize all different layers, including the provers, who is responsible for generating the zk proofs, as well as the sequencers, so that all of you have the validators to validate, and then the different one who can propose the blocks and then process the transactions. Okay, so just to reiterate, like for the community-driven, so these are like a subset of the contributors who has been contributed to the zkEVM circuit projects, and then there are like half members of like from school, and then like from Eastern Foundations and from other teams who like are very interested and contribute. So I think we'll just make it like continue going and then have a growing developer community to help us to build the zkEVM. And so just like share a bit our journey to scale the Ethereum. So Scroll is founded about like almost 2 years ago, and we've been like working for like about like almost a year, and then we until we reach the phase 1, and we believe that there's we build a zkEVM proof of concept that will make sure like putting the EVM into the zk circuit is a practical and is a possible things to do. And then after a few months, like we built our first pre-alpha testnet, like running like we are running both the layer 1 and layer 2s, and to just battle test like some of the zkEVM initial like ideas, and then running some of the provers to generate proof like at the real time. To share some of the statistics of our pre-alpha testnet, we like up to now like we have more than 1 million unique addresses running on our pre-alpha testnet. We have processed and executed more than 16 million total transactions. Have like built the proof for have proved for more than like 1.8 million blocks, and then we also receive like a lot of developers like deploy contracts on like there are 60,000 deploy contracts on the testnet from 36 different addresses. And fast forward to today, like on this Monday, February 27, we launched our alpha testnet. It's on a permissionless testnet on the GERDI. So though like for this new testnet, we'll be running like a more complete zkEVM circuits, and then we are connecting to the GERDI to more like having more real like the battle testing, and then have like a real like the GERDI test users to come and test on our testnet. So as like I said, like it's been live on the Monday, like it's been running like almost a week. We have like a zk proofs verified on the GERDI in the smart contract. It's like a being EVM equivalent. And then we also like build a bridge between the GERDI and the Scroll. And as of today, like I checked, like there's more than 12,000 GERDI ETH has been deposited through the bridge from GERDI to our Scroll testnet. And this is like some screenshot I took like the last night. So we already have like more than 130,000 addresses like been running, and we have already like within like the first week we already processed more than 400,000 transactions on our layer 2s. Okay, so that's like about like our story. So now I'm going to share some of the challenges in building the zkEVM and the zkROP. So where are the challenges you can think about like building those things? So first, you need to learn how to write zk circuits. And then writing zk circuits is harder than writing some regular normal programs. And then next, like after you learn how to write zk circuits, now you can build like zkEVM, like using the tools and then using all of the recent protocol, zk products, and then the open zk frameworks. And then last, after having the zkEVM, then you can build the infrastructure to run the zkROP, to build a proof and then to roll up and then to finalize on the layer 1s. So first, I will explain like why writing zk circuit is hard. Although like people know like writing zk circuit is hard, but like I think that fundamentally there are two reasons like the zk circuit is hard to write. So when you write a regular program, a normal program, so what do you need to do? Like, for example, you could want to write a function foo. You only need to think about like when you're taking the argument x and y and how to correctly compute the output z. So you only need to like write that program for like the computation correct, and then so that you can finish the program. But in the zk circuit, the logic is different. So you can think like both the inputs and the outputs of your original function becomes the input to your zk circuit. And then what circuit outputs really is that whether this input is a valid or not valid trace given the definition of your original functions. So that means like if you give a valid input like x, y, and then foo xy, then the circuit should output like it's a valid trace, and then that should last through. But if you're given like a different input, like a x, y, a z prime, like a random number, so the circuit should reject, and then you won't be able to generate a valid proof and then being verified by the verifier. So you should like think of it invalid. So what this entails is that when you're writing the zk circuits, you need to consider both the correct case and then some incorrect case. And then you need to prevent all of the incorrect case cannot pass through your circuit. That's like why like making writing the zk circuit is more tricky than writing your regular program. And then second things, like in the zk circuit, you need to work with the finite field. So what is a finite field? So it's just a field that contains a finite number of elements. So usually like the number is a prime number so that you can have some properties, like unique property from this prime number. So what does that mean? Like, for example, you can think like it's a modular. So all of the, like 1 plus something like a modular, a prime number will become a finite field. So take an example, like the finite field we're using to build the zkEVM is from a elliptic curve, BN254. And that finite field is a prime number of like a 254 bits value. Now the tricky things like in the EVM, the EVM word has like 256 bit values. That means like the EVM word cannot be natively represented inside a finite field. So in order to represent the EVM word, you need to split into two different numbers. For example, you can, a simple example is that you need to split into a high 128-bit value plus a low 128-bit value to represent the EVM word. So this is something like making like writing the zk circuits becomes a little bit more tricky than writing a regular program. Okay, now second, like if we know how to write circuits, and then we know like those challenges. So what's the challenging thing about writing the zkEVM? So if we consider zkEVM, before like we consider zkEVM, let's take the zk out and then look at how EVM works. So the EVM is the execution or interpreter that execute your smart contract bytecode like one by one, like sequentially. And if you look inside the Ethereum virtual machines, it has like a few components. First, you have an executor that interprets all of your opcodes and performs some of the computations. And then it also has like a stack and a memory for any transient data to be kept inside of the zkEVM, to keep inside the EVM. And then you also need to read the database to read the bytecode from a bytecode database, and then have a storage space that keep the user account and balance, and then also any like smart contract storage space will be keeping the storage. And then like user will send like a bunch of transactions, and it will process the transactions one by one sequentially. Now let's put the EVM back into the zk. Like what does that mean? Like how you build a zkEVM? So you also like build a zkEVM modularly, like the EVM. So first, if you look at the executors, you'll write an executor circuit, which right now we just call it the EVM circuit. So the EVM circuit is basically similar to what an executor behaves inside the EVM. It just processes all of the opcodes in your smart contract step by step, and then in each step, given like which opcode you are executing, you invoke a set of constraints to constrain that the computation has been done correctly. And then for the stack and the memory, you basically have a RAM circuit for any like a read and write. You'll put those read and write events into your records, like put into the circuit, and you can constrain that any like the read after the write at the same message, at the same address slot will become the same. And then third, for any bytecodes you load, you need to prove that you're loading the correct bytecode inside your zk circuits. That means you need to recalculate the bytecode hash that will be matched to the bytecode hash you stored inside your state account. For the storage, we know like the storage inside the Ethereum is like a Merkle-Patricia tree. So for every read and write, you will generate like a Merkle proof. So that means like in the MPT circuit, which stands for Merkle-Patricia tree circuit, you need to verify the Merkle proof for each read and write to your storage and account balance space. And then finally, when you process the transactions, you also need to verify that transaction you execute is a valid transaction. That means like you need to verify the transaction hash is correct, and then you need to verify your signature, the ECDSA signature of your transaction is also correct. And then we also know that Ethereum using the hash function to process to compute the transaction hash. So you will also have an individual hash circuit to verify the is calculated correctly. So like that, there's also a few other circuits inside the zkEVM. And then when you bundle everything together, then you get your zkEVM that can fully verify all of the transactions happen inside the layer 2 is correctly executed. Now, like let's say like if we have the zkEVM, how can we build the zkROP? How do we build the zkROP infrastructures? So let's also start from some simple example. So in the layer 1, the things like it's become more like straightforward. So the user just sending the transaction to the sequencer, and the sequencer will do some ordering of the transactions in the mempool and then process the blocks in the layer 1. Also, like I'm probably oversimplify this. Like you will have also consensus layers that do like more complicated things, but like the overall like the processing is like just having a single sequencers. Now, what happens inside the layer 2 is first, like it's more or less similar to the layer 1. So you have a sequencer that have like executor, so process all of the transactions. Then like the users like can submit the transaction directly to your layer 2 sequencers, but it can also submit any transaction from layer 1 bridge contract for any deposit or any enforced transactions that will go through the bridge. And then, so in the layer 2 sequencer, you need to build a watcher to watch any deposit events from your layer 1 bridge contract. Then, if you want to put up like a rollup, so that means like for a rollup, you need to send all of the data, like all of layer 2 data to be available on the layer 1, so anyone else can recover the layer 2 status by just reading the data from the layer 1. That means like inside the sequencer, you need to have a rollup agent to sending any data like in batches to the rollup contract that's located in the layer 1. And then like if you want to put the zkEVM, or like if for optimistic rollup, like you will have some fraud proof. So in the zkEVM case, like you have an extra node called a prover. So that's going to generate like running the zkEVM circuits, generate the proof, and then sending that back to the rollup to be verified and finalize any like batches, any transactions and blocks happened in the layer 2s. And why the prover has a separate node is because like running the zk provers is like a very heavy computation workload. So it means that you have like some dedicated beefy servers running either GPUs or very beefy CPUs, or even like in the future, they will be having some zk accelerators, ASICs, to run like to generate the proof within a small amount of times. And then inside the scroll, we also commit to decentralize. That means like then we have like a decentralized provers that are going to like generate those proofs. But we don't need to have all the provers like inside the scroll like to compete for each single slot. But you can randomly select a few provers so for availability, and then they want any of them like to generate a valid proof within the time limit. Then they can still like the layer 2 can still process and be finalized on the layer 1s. And then like even more complicated is like when you decentralize both the provers and the sequencers, then you need to have like a mesh network between the layer 2 sequencer and the provers. And for that, actually, we are still like working on some research ideas on how to decentralize both of the two sequencers and the provers. So if you are interested, like help us, you can also come and then work with us, or like just contribute and think about that. We are happy to collaborate with any community members. Okay, so that's like about all of our challenges we have. So what's our next step? And then I think we already have our alpha testnet, and then the next step is go to the mainnet. So we have like some roadmaps that we need to finish before we go to the mainnet. So first of all, to be fully transparent, so the zkEVM circuit we're running like in the alpha testnet is not like very complete. So I have like missing a few tiny things. One is like there are a few uncommon errors in the EVM we haven't fully constrained. And then we also like will add like a pre-compiles, support all the pre-compiled contracts in the zkEVM circuit. And we are already having a lot of things like work in progress, but we just are committed to finish that within like the next like few weeks. And then we are going to do like auditing, like we're going to audit the zkEVM circuits, the bridge contracts, and the node implementations. And then we'll also apply some of the optimization ideas we have, like to further reduce the proof generation time and then the proof generation requirements. And what's beyond the mainnet is like we're going to commit to do like this, trying to decentralize our provers in the beginning, and then to decentralize the sequencers, and then trying to build like a fully censorship resistant decentralized zkEVM mainnet. Okay, so this is last like the so help we are happy to have like more people to help us contribute to scaling Ethereum. You can join us, like you can have the hiring page, and you can also join and play with our pre-alpha testnet, and join our Discord to participate any, like if you have any questions you can join our Discord. We'll have people to support you. All right, thank you.